This is the notes for section 5.8, Systems of Inequalities. If you haven't done so already, make sure you pause the video at this time and read section 5.8 before going on with the video. So in this chapter now we've looked at inequalities in one variable. We looked at solving systems of equations. We looked at graphing inequalities involving two variables on a coordinate plane. Now what we're going to do is we're going to take those ideas and put them together and look at systems of linear inequalities. Okay? So when we're solving a system of linear inequalities, what we're really doing is we're finding an area or a region on the graph, and that region could end up being a polygon. It could be an open area that's just bounded by line segments and rays, or it actually could even be an empty set. But generally speaking, it's going to be a set of points, in a lot of cases an infinite number of points that can be represented by a region on a graph. Okay? In real life, we generally will refer to this as a feasible region. Example number 1, the Lions School Social Club is holding a flower sale. They will sell baskets of geraniums and petunias and plan to sell all the plants they have. Their profit on each basket of geraniums is $4 and on each basket of petunias is $2.50. If the club wants a profit of $500 or more, how many baskets of each kind of flower should they sell? Okay. Well, the first thing I want to do is I want to think about what I'm trying to figure out. I'm trying to find out how many baskets of geraniums and how many baskets of petunias the social club can sell. But the first thing I need to do the problem is I need to assign variables for the things that I'm trying to solve. So I'm going to start by just saying, well, let's let G equal the number of geraniums sold and P equals the number of petunias sold. Okay? Then the next thing that I want to do is I want to come up with a system of inequalities that are my constraints. Well, there's a couple things I know. Okay, one is I know about the profit. Okay, their profit has to be greater than or equal to $500. Well, I know that every time I sell a geranium, I'm getting $4, and every time I'm selling a petunia, I'm getting $2.50 in terms of profit. So I can write an inequality for that. Okay, so here's the system of inequalities. First of all, the inequality that I'm talking about, and that's 4 times geraniums plus 2.5 times the petunias, has to be greater than or equal to 500. That's the main inequality there. And then the other thing that I know is that the geraniums and petunias have to be greater than or equal to 0. I can't sell negative of either one of them. So this would represent the system of inequalities that I'm looking for. Okay? So then the next thing I'm going to do is I'm going to graph that system, because really the only way that I can show all of these, because there's really an infinite number of possibilities here, because it's not limiting how many that they could sell. So there's an infinite number of possibilities. What I want to do is I want to show that region graphically. So I'm going to graph each of these lines and shade in the region that would represent the feasible region. Okay? So if I graph those, the first one, 4G plus 2.5P, is greater than or equal to 500. Well, it's going to have a y-intercept of 200, because when G is 0, P would have to be 200. And it's going to have a g-intercept or an x-intercept of 125, because when G is 0, P would have to be 125. Okay? So I know that the shaded in, and we're talking about values that are greater than or equal to that, so it'd be all the values that are above that line. Okay? And then if I look at my other two inequalities, G is greater than or equal to 0 and P is greater than or equal to 0, all that does for me is it puts me in that first quadrant in terms of my solution set. So when I'm graphing this, I decided to stay within the first quadrant. So this gray region here represents my solution set. Now there's one other thing that we can't forget, and that is, although there's an infinite number of lattice points here, my solution set is actually lattice points. Okay, let's take a look at example 2 here. It says, consider the system y is less than or equal to negative 1/2 x plus 6, y is less than or equal to negative 2x plus 12, and then y is greater than or equal to 0, and x is greater than or equal to 0. Okay? Well, the bottom two equations, well, first of all, if we're gonna take a look at that system, it says graph the solution to the system by hand and check your solution. What are the vertices of the feasible region? Okay, so the area that would be our solution set, we're going to be looking for the vertices there. Well, first of all, the bottom two inequalities, y is greater than or equal to 0 and x is greater than or equal to 0, that limits us to the first quadrant. Okay, the other two, what we're going to do is this, is we're going to graph those as lines, and then we're going to look at where we're going to need to shade for all of the different inequalities that are there. Okay, so let's take a look at how we can do that. Okay, so to start out with, I'm going to take each of the graphs of the lines. So I have my x and y axis, so I drew those in. Okay, I have all of my lines graphed. The next thing that I'm going to do is I'm going to think about what the area would be that I'm shading. Well, I know that if it's less than or equal to for both of these first two inequalities, I know that it's got to be underneath both of those lines. Okay, and then if I look at y is greater than or equal to 0 and x is greater than or equal to 0, I know it's got to be above and to the right of those two lines. So that means if I'm satisfying all of those things, this gray area here would represent the feasible region for that system of inequalities. Now, the next thing that it asks you to do, and this is probably the more important question, is find the vertices of that feasible region. So you'll notice that the region that we ended up with was a polygon. Okay? And the vertices of that polygon are the intersections of lines. So for instance, this point right here, 0, 6, is its value, and the way I know that is that it's the intersection of the y-axis and this line y equals negative 1/2 x plus 6. And since 6 is the y-intercept of this line, it must be the intersection of those two lines. Therefore, that's how I'm getting the point 0, 6. Okay, so it's pretty easy to find that point right there. It's obviously easy to find the point 0, 0, the intersection of the x and y axis. And then finally this point over here, which is 6, 0, which is the x-intercept of y equals negative 12x plus 12, or negative 2x plus 12. The last point is a little bit harder to find. And that last point, which in this case is 4, 4, is the intersection of these two lines here. So what I'm going to do is I'm going to solve the system of these two equations. So if you take these two inequalities and make them equations, the vertex point would be the intersection of those two lines. Therefore, I'm looking to solve the system involving those two lines. So I'm going to go through and do that. I decided to use substitution to do mine. Okay, and when I use substitution, I've got negative 1/2 x plus 6 is equal to negative 2x plus 12. I solve for x, so x will be equal to 4. And then to find the y value, I'm going to plug 4 into either one of those of the equations of y equals negative 1/2 x plus 6 or y equals negative 2x plus 12, either one. I chose to put it into the negative 2x plus 12. If I do that, I get y equals negative 2 times 4 plus 12, therefore y would be equal to 4. So I found that the ordered pair 4, 4 is the intersection of these two lines. So I've now labeled all 4 of my vertices. That's going to be extremely important as we start looking at section 5.9, using those vertices to solve linear programming, which we'll get to in just a little bit. Okay.